Right now, 1.5 million kilometers from where you're sitting, a golden mirror the size of a tennis court is staring into the deepest darkness humanity has ever tried to see. And in the last few months alone, it has sent back images that should not exist. A galaxy that refuses to spin. A black hole so massive it shouldn't have had time to form. A cluster of galaxies crammed together. So early in cosmic history that astronomers are calling it, without exaggeration, a crisis in cosmology. NASA saw it. Oxford saw it. Texas A&M saw it. And one by one, the physicists who built our entire model of the universe are starting to admit something unsettling. The math isn't adding up. Stay with me, because tonight we're breaking down exactly what the James Webb Space Telescope just found, why it's dividing scientists across the planet, and why some researchers are now openly saying the universe might be older, stranger, and far more structured than we ever prepared ourselves to accept. Let's start with the machine itself, because you need to understand what makes this telescope different from everything that came before it. Launched on Christmas Day 2021, the James Webb Space Telescope is not just a bigger, better Hubble. It sees in infrared, which means it can look through walls of cosmic dust that block ordinary light entirely, and it can catch photons that have been traveling toward us for over 13 billion years. That's not a metaphor. When Webb looks far enough away, it is looking back in time, watching light that left its source before our own sun had even finished forming. Webb was built with fuel for a 10-year mission, but NASA's own engineers have since confirmed the launch trajectory was so precise it can serve so much propellant that current estimates now put its operational lifespan at 20 years or more, meaning this telescope could still be rewriting textbooks well into the late 2030s. And in just its first 4 years of science operations, it already has. Here's where the trouble started. Almost immediately after Webb began scanning the deep field in 2022 and 2023, astronomers noticed something that made no sense. They were finding galaxies, real, measured, confirmed galaxies, sitting at distances that placed them just a few hundred million years after the Big Bang. According to the standard model of cosmology, the one taught in every university on Earth, galaxies at that age should be small, chaotic, barely formed clumps of gas and newborn stars. Instead, Webb was finding galaxies that were massive, structured, some nearly as large as our own Milky Way, fully formed when the universe, by every calculation we had, simply hadn't had enough time to build them. Scientists gave this problem a name, the impossible galaxies crisis, and it hasn't gone away. If anything, it has gotten worse with every new observation cycle. In January 2026, researchers at Texas A&M University, led by Dr. Wida Hu, and published in the journal Nature Astronomy, identified what they nicknamed JWST's quintet, an active merger of at least 5 separate galaxies occurring just 800 million years after the Big Bang. Before this discovery, astronomers expected galaxy collisions on this scale to be rare and isolated events that wouldn't become common until well over 1 billion years into cosmic history. Instead, Webb caught 5 galaxies already tangled together, surrounded by a halo of oxygen-rich gas that could only have been produced and expelled by generations of dying stars. Professor Casey Papovich, who co-led the study, put it bluntly, "This discovery tells us our theories of how galaxies assemble and how quickly they do so need to be updated to match reality." Then, in June 2026, an international team led by astronomers at Leiden University and Oxford found something even stranger. Pointing Webb at a distant radio source called TGSS J5530 plus 1049, over 12 billion light-years away, they expected to find one growing galaxy anchored by a single black hole. What they found instead was a compact complex of at least 6 separate galaxies, 4 of them already surprisingly massive, packed into a region of space only a few tens of thousands of light-years across, all of it orbiting a rapidly growing supermassive black hole. Researcher Ayush Saxena of Oxford described it plainly. They didn't find a single galaxy. They found an entire construction site, hundreds of billions of solar masses of stars, crammed together and merging at a moment in cosmic history when the universe was supposed to still be a sparse, quiet, mostly empty place. And that's the pattern that should genuinely unsettle you. Not one anomaly, not 2. A growing list of observations, all pointing in the same direction, all suggesting the early universe was more crowded, more mature, and more organized than the model currently taught in classrooms allows for. Some astrophysicists argue this simply means star formation happened faster than we assumed. Others aren't so sure that's the whole story. Because the deeper Webb looked, the more it found that shouldn't have been ready yet. Massive galaxies, ancient mergers. And then, in May of this year, something even more bizarre. A galaxy so early, so massive, that it broke one of the most basic rules of how galaxies are supposed to behave at all. In May 2026, a team at the University of California, Davis, led by research scientist Ben Forrest, published a finding that even seasoned astronomers described as deeply strange. Using Webb, they examined a massive galaxy known as XMM Vid 1 2075, formed less than 2 billion years after the Big Bang. And when they measured how the stars inside it were moving, they found almost nothing. No rotation, no spin. The galaxy just sat there, its stars drifting in seemingly random directions instead of orbiting together in the organized, disk-like motion we see in nearly every other galaxy of comparable size, including our own Milky Way. Here's why that matters. Rotation isn't a cosmetic detail. It's a fingerprint of how a galaxy formed and evolved, built up gradually over billions of years, as gas collapses, spins up, and settles into a stable disk. That kind of smooth, organized rotation is something astronomers associate with old, mature, fully evolved galaxies, the kind you'd expect billions of years later, not less than 2 billion years after the universe began. Forrest's team confirmed this wasn't a fluke. Previous observations had already shown XMM Vid 1 2075 was one of the most massive galaxies known from this early era, already containing several times as many stars as our entire Milky Way, and already finished forming new ones. A galaxy that should have been young, chaotic, and still spinning itself into shape was instead behaving like something ancient. Forrest and his colleagues examined 2 other galaxies from the same cosmic period for comparison. One rotated normally, one showed irregular, disorganized structure. But the third showed no rotation at all, just strong, scattered motion of its stars, as if the normal rules of galactic assembly simply hadn't applied to it. Around the same period, a second mystery was deepening, this one involving black holes. Webb has now confirmed the existence of supermassive black holes present just 500 to 700 million years after the Big Bang, and these aren't modest objects, they're black holes, with masses that, under standard models of gradual accretion, where a black hole slowly grows by consuming gas and merging with smaller black holes over billions of years, simply should not have had enough time to reach the size Webb is measuring. Something had to jumpstart them. Some researchers now argue this points to what's called direct collapse, massive clouds of primordial gas collapsing straight into a black hole without ever forming a star first, skipping millions of years of the process we assumed was mandatory. Others aren't convinced that explanation covers the full scale of what's being found. Either way, the conclusion is the same. Our understanding of how black holes are born may be fundamentally incomplete. And then there's the phenomenon astronomers have started calling, almost affectionately, little red dots. These are compact, intensely luminous objects scattered throughout Webb's deepest images, and nobody agrees on what they actually are. Some researchers believe they're impossibly massive, impossibly compact galaxies. Others argue they're active galactic nuclei, supermassive black holes feeding so aggressively that the surrounding material glows in dense, tiny points of light. A newer and stranger idea has even entered the conversation, that some of these red dots might be something in between, objects some scientists have started calling black hole stars, a category that didn't exist in astrophysics textbooks even 3 years ago. Whichever explanation turns out to be right, every single option creates new problems for the models we've relied on for decades. Now, you might be thinking, all right, the early universe was busier than expected. Fine. But here's where it gets genuinely strange. Because alongside all this unexpected abundance, unexpected structure, unexpected maturity, Webb also found the opposite. Massive galaxies that formed fast, burned bright, and then died shockingly young. In June 2026, astronomers combining Webb data with the Atacama Large Millimeter Array uncovered evidence of what they're calling a galaxy-killing wind, a powerful outflow of gas triggered by cosmic mergers, violent enough to strip a galaxy of the raw material it needs to keep forming stars. This may finally explain a mystery that's puzzled astronomers for years. Why so many massive galaxies in the early universe appear to switch off, going quiet and dormant far sooner than any model predicted they should. So pause and take in the full picture, because no single headline captures it. In the space of just a few years, Webb has found galaxies too massive to exist this early, a galaxy too still to be this young, black holes too large to have grown this fast, mysterious red points of light nobody can definitively classify, and violent winds capable of killing off galactic growth almost as soon as it begins. Every one of these findings on its own might be dismissed as an outlier, a strange corner case future data will smooth over, but together they form a pattern that keeps repeating across different teams, different instruments, different corners of the sky, always pointing toward the same uncomfortable conclusion. The universe, in its first billion years, was not the slow, quiet, gradually assembling place our models described. It was fast, it was violent, it was, in some cases, disturbingly organized. And this is exactly the environment that set the stage for what may be Webb's most controversial finding yet, one that didn't come from a distant galaxy at all, but from a single, strange little planet just 124 light years from Earth, where scientists caught a molecule that, on our own world, has only ever meant one thing. Let's talk about K218b, because if you've been anywhere near science headlines over the past year, you've probably heard fragments of this story, but almost certainly not the whole picture. K218b sits 124 light-years away in the constellation Leo, orbiting a small, cool, red dwarf star. It's 8.6 times more massive than Earth, and it orbits inside its star's habitable zone, the region where liquid water can exist. Scientists believe it may belong to an entirely new category of world called a Hycean planet, a massive ocean hidden beneath a thick, hydrogen-rich atmosphere. Not a rocky world like ours, a water world, larger than Earth, wrapped in an alien sky. In 2023, a Cambridge-led team pointed Webb at this planet and detected methane and carbon dioxide with 5 sigma confidence, the gold standard in astrophysics, essentially near total certainty. But buried inside that same data was something else entirely, a faint, tentative hint of a molecule called dimethyl sulfide. On Earth, this compound is the smell of the sea, produced almost entirely by marine phytoplankton. There is no significant geological process on our planet that manufactures it. Life does, which is exactly why astrobiologists have listed it for years as one of the most promising biosignatures we know how to look for. Then in 2025 and into 2026, the Cambridge team returned with a second independent instrument and found stronger hints of the same molecule alongside a related compound at roughly 3 sigma confidence. Headlines exploded worldwide, but NASA's own reanalysis of the data placed the confidence closer to 2.7 sigma, well below the 5 sigma bar science demands for a genuine discovery. MIT's Sarah Seeger warned publicly that enthusiasm was outrunning evidence, and researchers pointed out something the celebratory headlines conveniently skipped. Dimethyl sulfide has also been detected in comets and in the cold, dead chemistry of interstellar space, places no living thing has ever existed. As of today, the honest answer is that nobody knows. The signal hasn't been confirmed. It also hasn't been killed. It's sitting exactly on the edge between detection and illusion, and researchers are already lining up more observation time to try to settle it once and for all. But K218b isn't the only place where Webb caught something that made scientists pause and double-check their instruments. In one of the more surreal images to come out of Webb's deep field surveys, astronomers captured what's known as an Einstein ring, a phenomenon where a massive foreground galaxy bends the light of a more distant galaxy directly behind it into a glowing circle. Gravitational lensing itself isn't new. Einstein predicted it over a century ago, and we've observed it many times. But the ring found around a distant galaxy, catalogued as J418, was different. It was nearly perfect, a full, uninterrupted circle of light, requiring an alignment between 2 galaxies so exact, down to fractions of a degree across billions of light years, that researchers openly called the odds of it forming this cleanly by pure chance statistically remarkable. Elsewhere, Webb turned toward regions of space that, by every visible measure, should be empty. No stars, no galaxies, no detectable mass. And yet, light from more distant background galaxies was bending, curving, and distorting as it passed through. Exactly the signature you'd expect if something massive but invisible were sitting there. Astronomers have tentatively attributed this to dark matter, the mysterious, unseen substance that makes up roughly 27% of the universe's total mass and energy, according to current cosmological models, but which we have never directly detected, only inferred through its gravitational effects. What's caught researchers' attention is the shape and intensity of the distortion in these particular patches of sky. Rather than behaving like a diffuse, evenly spread cloud, the way dark matter is generally modeled, the lensing in some of these regions behaves more like a discrete structure with defined edges and concentrated mass. Is it simply a denser than usual clump of dark matter? Almost certainly, according to most cosmologists. But the fact that we still cannot directly image, touch, or fully explain the substance responsible for a quarter of everything in existence tells you how much of the universe remains, quite literally, invisible to us. Meanwhile, not every Webb discovery this year has pointed toward mystery. Some have pointed toward hope. Throughout 2025 and into 2026, Webb has been steadily building out a chemical inventory of exoplanet atmospheres across dozens of distant worlds, detecting carbon dioxide, water vapor, methane, and sulfur dioxide on planets we could never have studied in this kind of detail before. In the TRAPPIST-1 system, just 39 light-years away, 7 Earth-sized planets orbit a small red dwarf star, and observations of TRAPPIST-1e, the planet sitting most comfortably inside the habitable zone, have revealed spectral signatures consistent with a thin atmosphere containing carbon dioxide and traces of water vapor. Not confirmed habitability, not proof of anything, but another small, careful step narrowing the field of candidates where the conditions for something extraordinary might exist. So here's where we stand today, in the middle of 2026. A telescope built to look backward in time keeps finding a universe that grew up too fast. Galaxies too massive, too early, too structured, too still. Black holes too big to have formed on schedule. A possible ocean world with a maybe biosignature that refuses to resolve into a clean yes or no. And an invisible substance shaping the sky in patterns we can measure but still cannot see. Individually, each of these is a fascinating footnote. Together, they start to look like something else entirely. A universe quietly telling us that the rulebook we've been using for the last 100 years might need to be rewritten from the ground up. So where does all of this actually leave us? Sitting here in July 2026, watching a $9 billion mirror stare into the dark and keep sending back data that doesn't fit the models? Here's the honest answer, and it's more interesting than any single headline. We are not looking at one broken theory. We're looking at the accumulation of dozens of small cracks, each one on its own explainable, each one together forming something that looks a lot like a genuine turning point in how we understand the universe's early history. Let's connect the dots one more time, because this is the part most coverage rushes past. Webb found galaxies far too massive and structured to exist within the first few 100 million years after the Big Bang. It found an active 5-galaxy merger, occurring just 800 million years in, when the universe was supposed to be sparse and quiet. It found a compact complex of 6 galaxies, 4 of them already massive, crammed together 12 billion light years away, building a supermassive black hole in real time. It found a galaxy that refuses to spin, behaving like it's already ancient when it should still be forming. It found black holes so large, so early, that standard accretion models cannot explain how they grew that fast without some entirely new formation pathway. And it found a violent galaxy-killing wind capable of shutting down star formation almost as quickly as it begins, potentially explaining why so many of these early giants burned out young. None of these findings, on their own, breaks physics. But stacked together across independent teams, independent instruments, and independent corners of the sky, they paint a picture cosmologists did not expect to be painting in 2026, a young universe that behaved like it had already lived several lifetimes. And then there's K2-18b, still sitting in scientific limbo. Its possible biosignature neither confirmed nor dismissed, waiting on more transit windows and more telescope time before anyone can say anything with confidence. There's the Einstein ring so close to geometric perfection that its odds of natural formation left researchers double-checking their math. There's dark matter, casting shadows with edges we can measure, but a substance we still cannot see, touch, or directly detect after decades of trying. Individually, cautious footnotes. Collectively, a universe that keeps declining to behave the way our equations insist it should. Now, to be clear, because this matters and because real science deserves real context, not one of these findings has been declared proof of anything beyond natural, if still poorly understood, physical processes. The scientists behind every single discovery in this video have been careful, deliberate, and cautious in how they've presented their work. Ben Forrest didn't claim his non-rotating galaxy defies physics. He called it a trait that challenges current theories of how young galaxies form. Casey Papovich didn't claim the universe is impossible. He said our models of galaxy assembly need updating to match what we're actually observing. That distinction matters. This isn't a story about broken science. It's a story about science doing exactly what it's supposed to do, running headfirst into data that doesn't fit, and having the honesty to admit the old answers aren't good enough anymore. But here's why you should still be paying close attention, because this crisis in cosmology is nowhere close to finished, and the next few years are going to bring a wave of new data specifically designed to settle it. The Vera C. Rubin Observatory, now conducting its full sky survey from Chile, is expected to massively increase our detection rate of transient and distant cosmic events. NASA's Nancy Grace Roman Space Telescope is targeting a launch by 2027, potentially sooner, built specifically to survey wide fields of the sky for exoplanets and dark matter distribution at a scale Webb was never designed for. European Southern Observatory's extremely large telescope, under construction in Chile with a mirror unlike anything ever built, is scheduled for completion in 2029, and it will be capable of directly examining the kind of early, massive, structured galaxies that are currently breaking our models, with a level of precision that could finally tell us whether we're looking at faster star formation, new physics, or something else entirely. And behind all of it looms NASA's Habitable Worlds Observatory, still in early planning, but built around a single explicit mission. Not mapping galaxies, not studying dark matter, directly imaging Earth-like planets around sun-like stars and analyzing their atmospheres for the exact kind of biosignature still hanging in question over K2-18b right now. Think about the position we're actually standing in. For the first time in human history, we have a telescope powerful enough to catch the universe contradicting itself. and an entire generation of new instruments already being built specifically to chase down every one of these contradictions to its source. We're not waiting decades for the next clue. We're watching the clues arrive in real time, one Nature paper, one press conference, one impossible galaxy at a time. So here's what I want you to actually sit with tonight. Every one of these anomalies, the spinless galaxy, the 2 massive black holes, the 5 galaxy merger, the maybe biosignature ocean world, the near-perfect ring of bent light, exists because we finally built an instrument sharp enough to notice them. For every mystery Webb has already handed us, how many more are sitting in data we haven't finished analyzing yet? How many are waiting in the next deep field image, the next transit of K2-18b, the next galaxy cluster nobody has pointed a telescope at yet? We are living through the exact moment when our tools finally caught up to our questions, and the universe is answering back faster than our textbooks can keep rewriting themselves. So I'll leave you with this. If galaxies really did grow up this fast, if black holes really did skip the queue, if the early universe really was this crowded, this violent, and this strangely organized, then everything we teach students about the first billion years of cosmic history needs a serious rewrite, and it's already underway. Do you think we're looking at gaps in our models that better data will eventually smooth over? Or are we watching the first real cracks in a theory that stood for almost a century? Tell me what you think in the comments, because this debate is not settled, and it is not going to be settled quietly. Subscribe and turn on notifications, because the next Webb data release could land any week now, and when it does, you're going to want to already be here when the universe changes its story again.